All right, hello everyone. Today is July 12th, 2022. We are going to be going over the chapter 13 homework. We're going to complete it. We're going to be working on the second half of it. We're going to start on question 17. The homework is due today. So, if you are listening asynchronous, the homework is due today. So it is your responsibility to get the homework done. So without further ado, we'll go to question 17. Question 17 says draw the major product formed. Whenever you have, let me go back. Whenever you have some type of epoxide, we have HBr. So this is going to take a proton from the HBr. Those electrons are going to release that to the bromine. And since this is a tertiary, this is in the tertiary position. That's going to come here, and we'll have the electrons released to the oxygen. So if we do that, then we're going to have, this is our major product. All right, so that's 17. Let's take a look at 18. So MCPBA, we can do 18 on the same slide. MCPBA will add an epoxide. That's metachloroperioxybenzoic acid. What we're going to get is a transdiol. We're going to get the transdiol enantiomers. I wonder, and it says only draw one enantiomer, so you're going to get, you're going to form the epoxide, and then you're going to add, your alcohol to this and a trans. If you want to draw the other enantiomer, that's fine. But it only requires one enantiomer. So if you draw both, it's going to mark it wrong. So please don't do that. If you want to draw the other enantiomer, please go ahead. And I drew these in the wrong position. They should just be one more down. Oh. Here. This. So 19 is very similar to 17. So I'm looking at question 19. It's really similar. And we have HBr. So this epoxide right here is gonna take a hydrogen from the HBr. That's gonna be released, and then we just have to figure out where the attack is gonna occur. And then we'll have an inversion. So we have a nucleophilic substitution, which inverts the configuration on the substitution site. So instead of going down, so we'll draw the product how it should be. Like I said, this is very similar to 17. So we have this. Instead of this going, this was, so we have to have a solid wedge here. I'm not the best drawer, but I try my best. This is going to be now going in, bromine. This is what you're going to want to draw. That's 19, very similar to 17. And once that bromine's come off, it's going to have a nucleophilic attack right here. And that's how you get the inversion right there. So question 20, we can put this on the same slide in case you're still working on 19. This is give the systematic IUPAC name for the given molecule. This is going to be 1-pentane thiol. And it's a thiol because we have a sulfur and it occurs at the 1 position. So that wasn't too bad. We can even put 21 here. They show us this right here. And anytime you see an oxidation, you're going to form a disulfide or a sulfide-sulfide bond. So this is going to yield same thing. Now we just have a sulfur bond right there. So we're going to put this for 21. So if you see an oxidizing agent such as O2 or I2, this is going to give you your disulfide. 22 is pretty simple. It just says draw dimethyl sulfide. So this is it. That's dimethyl sulfide. All right. It's 22. So 23, it says consider the reaction 1s3s1-chloro-3-methyl-cyclopentane and methane thiol. In the presence of sodium hydroxide, draw the organic product and clearly indicate the stereochemistry, and then analyze the stereochemistry of the products. So we can go to a new slide for this one. Cyclopenyl group. We got this methyl coming off right here. This. So this is the good leaving group right here. This is where our attack is going to occur. We have this in a presence of a strong base, so that methyl thiol will be deprotonated, and this will come here and attack as an SN2. This will be gone, and then we'll have inversion. We'll invert our configuration right here. So this is what we'll get for a final answer. We leave the configuration here. We're going to invert it here. So now it's going to be solid. We have this. So whereas it was an S, now it's going to be an R. So we're going to have, this is going to be R, and this is going to be S here. It's S, and this is, yep. So we're going to put 1R, 3S, that's going to be chiral. You have to check those two boxes. All right, so that was 23. Let's go to 24. So we are in the three-step synthesis. We just have to select the answer box. So my first step for the reactant, let's see. This. And my R1 will be that. My step 1 product will be this. And my R2 will be this. My step 2 product will be that. R3. And my final product will be that. It's 24. All right. If you have any questions, hopefully you're getting them all correct. So we'll go on to 25. Kind of like 24, we just have to select the correct reagents. So R1, we're going to have C6, H5, CO3, H, and dichloromethane. R2, we're going to add that phenyl group to it. So we have C6H5, lithium, and ether, followed by a protonation. And R3, we're going to have PCC and CH2Cl2. So first we're going to form the epoxide. So you're going to form your epoxide step with this one. Then you're going to add that phenyl group to it. So that phenyl group is going to come in and do an attack. And then you're going to use PCC. What's going to happen with PCC is you're going to have that phenyl group here. You have this OH, and that PCC converts this into a ketone. So now we have our ketone. So that's why we go in the order we're doing. All right, so let's go to 26. So we have to identify 3 different reagents. So the first one we're going to use NaH because that hydride is going to pull the hydrogen from the alcohol group, and that's going to release the electrons. Then we're going to use ethylene oxide. So we're going to use ethylene oxide. And you can see kind of how this is going to go like that. This will happen. And we're going to use PCC to convert this alcohol into, it'll convert it into the aldehyde right there, since it's on the end. And that's it for that one. All right. So let's go to 27. 27 has 6 different steps. The first thing we're going to do is we're going to add bromine. And once we add our bromine to it, we can get rid of that bromine. Now, if we have bromine right here, you can get rid of it through an elimination reaction. And what are you going to use for elimination? You're going to use CH3, 3CO. You can just imagine this coming in like this and eliminating that right there. So that's your step 1, this is your step 2. So now your step 3, you're going to create your epoxide. How do you do that? Well, you're going to use MCPVA. Then you're going to do an attack. You can do attack with this anion. Fifth, you're going to protonate this this oxygen right here. So you're going to protonate this. And how are you going to protonate it? Well, you're going to use water and then mild acid. Write that down. Lastly, how do you take an alcohol to a ketone? In this case, right here, we're going to turn this into a ketone. We're going to use PCC. All right, so let's go to do the last one. 28. We're going to use magnesium to create the Grignard reagent. Step 2, we're going to add this. Step 3, we're going to pronate it. Step 4, hydride addition. Step 5, we're going to use CH3, CH2, CH2, bromine. Basically how this works, I'm going to get my pen out and show you it too. So you form that Grignard reagent, right? I'm just going to draw it like this because you have NGBR. This is going to go attack. Let's see, which end am I going to attack on? Yep, so draw this here like that. Attack here, we'll release this here. And then this is going to form an SN2 reaction here. So bromine, that's a good leaving group. And that's how you get your final product. All right, so that's it. We'll come back at 10:50 and we will start chapter 14. All right, everyone, we're going to resume the lecture. Welcome back, everyone. Chapter 13 homework has already been posted to Blackboard, so you have it. This lecture will be posted to Blackboard as soon as we're done. So really, if you're listening asynchronously, there's really no excuse for not getting your homework done today. So please get it done. That way, you are staying on top of things. So let's get into chapter 14. Chapter 14 talks about IR spectroscopy, infrared spectroscopy. It goes into a little bit of mass spectrometry. Just to let everyone know, I taught a class, and I'll share my screen. I taught a class this past spring just based on mass spectrometry, and it was a semester-long course. and we couldn't even finish everything in that semester-long course because there's a lot to do with mass spectrometry. So you can only imagine, you're just getting a little taste of mass spectrometry today. It's only half a chapter, so there's much more to mass spectrometry than what you're going to learn, but at least it gives you a little basics about what's going on. So why do we study spectroscopy? Really, I don't want to read off the slide, but you really study spectroscopy because you want to identify some type of compounds. That's the whole point of the mass spectrometry and the infrared spectroscopy. It's just to help you identify, the difference between cocaine and maybe an analog of cocaine, or, maybe you are analyzing what I did when I worked for the USDA. I used mass spectrometry to analyze mycotoxins, and it helped us identify, and mycotoxins are mold basically found in grain. So it helped us identify that. It says, it gives you the electromagnetic spectrum, showing you where the near IR and the infrared is. And I'll get my pointer out. You can see the near IR and the infrared right here. And for IR, that's the region that we're going to be talking about. I don't know if we've gone into it yet or not, but at some point in time, maybe in general chemistry, you talked about UV visible spectrometers, and that's the range right here. But we're going to be in the near IR and the infrared. It says different regions of the electromagnetic spectrum are used to probe for different aspects of the molecular structure. The radio waves is NMR, infrared is IR, UV vis can use visible and ultraviolet. You can also go into the near IR for both IR and UV vis. It's on the, if we're on the UV vis, the near IR is right here. If we're on the infrared, the near IR is right here. Some instruments are capable of going into that region for those instruments. I don't want to go too much into this, but it says matter also exhibits wave-like properties. It says for electrons in covalent bonds, vibrational energy levels are separated by gaps. If a photon of light strikes the molecule with the exact amount of energy needed, the light is absorbed and vibrational excitation will occur. And there's different energies that occur with IR. IR spectron. So we have molecular bonds can vibrate by stretching or by bending in a number of ways. We can see the stretching right here. We see the bending, the vibration, the scissoring, and you can have a twisting. So this one's, let me get my pen out here. So if this one's coming this way, this one's going back into it. And these are scissoring, so they're both coming in the same direction. You can see the stretching right here. And it gives you some practical examples such as night vision or the ability to detect breast cancer. So the energy necessary to cause vibration depends on the type of the bond. There will be differences between the CH bond and the CO bond. You have a smaller energy gap right here. You have a larger energy gap right here, and there'll be differences where they show up in different intensities as well. There's an IR spectrophotometer. It irradiates a sample with all frequencies of IR light. The frequencies absorbed by the sample tell us the types of bonds and the functional groups that are present. It says most commonly sampled or deposited on salt. That's not true anymore. And they used to make these KBR pellets, but these KBR pellets are really difficult to make. Oftentimes they'd break. In all practicality, all you have to do is put your substance on a little plate like this. You put your substance on here, you put the ampoule down, you take the IR spectrum. It works by attenuated total reflectance. So you don't have to prepare these salts or these KBR pellets anymore. It's just you put the sample down, You shoot it, and then you get the spectrum. So then you'll get a spectrum like this. Obviously, this wouldn't work for a gas. You know, if you had a gas, then you'd have to put it in some type of gas cell, you know, but it does work for solids and liquids. It says an IR spectrum plots the percent transmittance as a function of frequency. The peaks are called absorption bands. You can see many different absorption bands with a percent transmittance. There's units of frequency in IR called wave numbers. The values range from 400 to 4,000. So we have from 400 to 4,000. So we have characteristics, wave number, intensity, and shape. And for those interested in the math about it, here it is. It says the stronger the bond, the higher the stretching frequency. The larger the mass difference, the higher the stretching frequency. I'll give you some examples right here. This would be a pretty strong bond right here. And this would be a pretty weak bond. This wave number formula and empirical observation allows us to designate regions as representing specific types of bonds. So you'll have regions that, you know, just have carbon-hydrogen bond, triple bonds, double bonds, and single bonds. It says the region above 1500 is called the diagnostic region. The peaks in this region provide clear information. We're talking about this region right here, clear information. The region below 1500 is called the fingerprint region, and there are typical of many signals here, and it's difficult to analyze. So right here, but this might be where you need to look though for some compounds. So here we have two similar peaks. It says because they have the same type of covalent bonds, you know, they both have alcohol groups. They're slightly different though. And this one has one more carbon here. The R spectra for 2-butanol and 2-propanol are virtually indistinguishable. So you're going to have to blow up one of the regions to see, you know, where it occurs. See on this one has this that's missing. This one has this right here. And you can go in the fingerprint region too to distinguish the two. So compare the IR stretching frequencies for each carbon-hydrogen bond below. So as it becomes a more S character, what do we mean by S character? If you recall from organic 1, you know, this would be 50% S, this is 33, and this is 25. So as we increase in S character, we shift down, don't we? So the higher the S character of the carbon, the stronger the carbon-hydrogen bond, and so the higher the stretching frequency. All right. This alkyl carbon hydrogen bonds come just under 3,000, while alkenyl and so double bond and triple bonds are over 3,000. You can see that right here. This one's coming above 3,200. This one's coming a little after 3,000. This one comes below 3,000 on the alkane. So it is possible that an alkene or alkyne could give an IR spectra without any signals above 3,000. So there's no signal here at 3,100 and no signal at 3,300. And that's because there's no carbon hydrogen bond. So resonance or delocalization, we can see we have resonance here. We draw these electrons here, put them up here, and they can come back down, push that double bond back. So the resonance or delocalization of electron affects the strength of a covalent bond and thus the wave number of a stretching. So consider the carbonyl stretching value for the following compounds. So we see we have a ketone and we have a conjugated ketone. This one has resonance. And you can see we shifted that number down, didn't we, by 40. So the more delocalized the p electrons, the weaker the p bond and the lower the stretching frequency. And we saw that with the conjugated ketone, lowering it from 1720 to 1680. It says conjugated carbonyls have lower stretching frequencies. You see that? Here, this one's lower. This one's 1710 versus 1680. And we see an esters at 1740. So the strength intensity of IR signals can vary. And you've seen that, if we come up here, we see different intensities and strengths. This is when a bond undergoes stretching vibration, its dipole moment also oscillates. I recall the formula for dipole moment includes the distance between the partial charges. The oscillating dipole moment creates an electric field surrounding the bond. And where are we going with this? So the greater the bond polarity, the stronger the IR signals. So we see we have a partial positive here, partial negative here. We have a greater bond polarity, so we're going to have a stronger IR signal. We can see that right here. So note the general, so we can see that here we have more bond, this one has greater bond polarity. And it's a stronger signal. So if a bond is completely symmetrical, then a stretching frequency is not observed in the IR spectrum. Here, this is all symmetrical. It says if then a stretching frequency is not observed in the IR spectrum here. It says stronger signals are also observed when there are multiple bonds of the same type vibrating. Although carbon-hydrogen bonds are not very polar, they often give very strong signals because there are often many of them in an organic compound. It says because sample concentration can affect signal strength, basically this toxalyzer, which is a breathalyzer, can be used to determine blood alcohol levels by analyzing the strength of carbon-hydrogen bond stretching in blood samples. These are blood alcohol levels, not breathalyzers. Sorry, the book does talk about using this as a breathalyzer too, though, in this chapter. So some IR signals are broad, while others are very narrow. OH signal is stretching. So the usually no OH stretching are often quite broad, and you'll see this. So when possible, OH bonds form, can do hydrogen bonding that weakens the OH bond strength. And yeah, the hydrogen bonds are transient, so the sample will contain molecules with varying OH bond strengths. It says, but the OH stretch signal will be narrow if a dilute solution of an alcohol is prepared in a solvent incapable of hydrogen bonding. Here's where you usually see your OH bonding right here, your OH group. So it's possible to see two signals for an OH bond, one for the free OH and one for those engaged in hydrogen bonding. So here we have hydrogen bonding, and here we have the free OH. And you do typically see this. You can get rid of this. Let's just say you because most likely, where do you think this is coming from? A lot of times this is coming from water in the atmosphere. So, the atmosphere is mostly composed of nitrogen, but there's a lot of water in there. So what you can do is we don't have this here, but I've used it elsewhere. You can pump out the air, and you can pump it in with nitrogen N2. So you can get rid of that OH peak if you want, if you have the capabilities. And you may want to get rid of that OH peak so you can make sure that if you're seeing an alcohol, that it's coming from your compound, not just water, in the room. So consider how broad the OH stretches for a carboxylic acid and how its wave number is around 3000 rather than 3400 for a typical OH stretch. Here we have more of a broad peak. It's more narrow right here. Says carboxylic acids, hydrogen bond is often more pronounced in carboxylic acids because they can form hydrogen bonding dimers. We can see that right here. Primary and secondary amines exhibit NH stretching signals. Remember, there's 3 types of hydrogen bonding. You can have NH, OH, and FH. Because NH bonds are capable of hydrogen bonding, their stretching signals are often broadened. So secondary amines exhibit only 1 signal for NH bonds, while primary amines exhibit 2 signals. And they're going to give us some example spectra on the next slide, but I'll leave this up here in case you're taking notes. So here we have a primary amine, and here we have a secondary amine. So you see the 1 signal for the secondary amine, you see the two signals for the primary amine right here. So the 2 NH bonds vibrate together in 2 different ways. So we can have symmetric stretching and asymmetric stretching. So that's how we're giving rise to the 2 signals, by the 2 stretching types of stretching. Table 4. So there's a table in your book that will summarize some of the key signals. So you don't have to memorize all this stuff. Please use the tables to to answer any questions regarding IR spectra. It says focus on the diagnostic region. Remember, that's the region above 1500. 1600 to 1850, check for double bonds. 2100 to 2300, check for triple bonds. And 2700 to 4000, check for XH bonds. It says when looking at the 2700 to 4000 region, draw a line at 3000 and focus on the signals that come above it. So IR spectroscopy is used to determine the success of reactions. So we can use it to determine if we, turn this alcohol into a ketone. Remember, we did this. Does anyone remember what reagent we used in our homework? We used PCC as one possible reagent for that. So now they're talking about mass spectrometry. Remember, I did teach a whole semester class on this, and here you're just seeing a half a chapter. So there's a lot more to it than just this half a chapter that you're seeing, but it gives you a introduction to it. So mass spectrometry is primarily used to determine the molar mass and formula. And oftentimes we use these techniques together with each other in conjunction as confirmatory techniques. In a mass spectrometer, a compound is vaporized, then it's ionized, and then it undergoes fragmentation. The mass of the ions are detected and graphed. So, first let me get my pen out. So you have your sample. It can be a liquid sample. It can be a solid sample. It can be a gas sample. So let's just say it's a liquid sample, then you're going to vaporize it, so you have to somehow heat it up. And once it's vaporized, it's going to be a gaseous stage, and then you're going to ionize it. You're going to hit it with something to ionize it. So it's going to be that. What do we mean by that? It's either positive or negative. If it's neutral, it's not going to go through the mass filter. Then you're going to separate it out through some type of mass analyzer. And it does undergo fragmentation. And the mass of the ions are detected. So then you have a detector right here, and it's going to detect those ions. The most common method of ionizing molecules is by electron impact. You'll most likely see this on a GC-MS. The sample is bombarded with a beam of higher energy electrons. And that's going to hit your sample right here. So you're going to have these electrons. They're going to hit this. We're going to break this up and you get a radical cation. The mass of the radical cation is the same as the parent compound. So this should be the same mass. If the radical cation remains intact, it is known as a molecular ion or the parent ion. They more commonly now call it the molecular ion. This is the old name right here, but we've moved to the now calling it the molecular ion. Most of the radical cations typically fragment into a radical and a cation. The ions are deflected by a magnetic field, and their mass to charge ratio is detected. So remember, you have this mass analyzer. They're going to go through, and their mass to charge ratio is detected. It says neutral. So if it's neutral and it doesn't get fragmented or radical, it's not going to go past. It's not going to go through this mass analyzer. It's just going to go. It's just going to shoot right there. Here, this is one of the most common, most basic compounds there are, just methane. This is the base peak. So if you count methane, what is this? 12. This is 16. Here we have 16. We have a peak right here. You may guess, you may know why we have that peak right there, because you have carbon 13. Carbon 13 has how many protons? 6 protons and 7 neutrons. This peaks with a mass of charge less than the fragment, less than the parent or the molecular ion, represent fragments. The subsequent H radicals can be fragmented to give the ions with 12, 13, 14. And you saw this right here. We have 15, 14, 13, and 12. So it's a sensitive analytical technique, can be used in many different types of industries, and that's what they're showing right there. So here's the mass spectrum for benzene. So what is this? Each one has a hydrogen. So I have 1, 2, 3, 4, 5, 6. 6 times 12, that's 60, 72. And then you got plus 6 is 78. You'll have fragmentation. That's how you go down here. It says for most compounds, the M plus peak is not the base peak. So you can see, let's just count this. Okay, we have 5. This is pentane. So 5 carbons times 12 equals 60. And then how many hydrogens you have? 3, 2, 2, 2, and 3. So 3, 6, 8, 10, 12, 72. somewhere around here. I don't know which one's 72 here, but somewhere around there. But notice that, you know, that's not, so the base peak is the one with the highest one right here. And, you know, they're saying that the parent peak comes over here, the molecular ion peak comes over here. So some people might think, you know, oh, this is the you know, molecular ion, it should be 100%, but in this case, a fragment peak is. I don't know why they keep on calling it the parent peak when they put it in bold, the molecular ion peak. So the mass to charge of the molecular ion is the molar mass of the compound. Parent ion and molecular ion are interchangeable. An odd mass peak generally means there is an odd number of nitrogen atoms in the molecule. An even mass peak generally indicates an absence of nitrogen or an even number of nitrogen atoms. So here we have odd number right here. We have two even numbers, and we have 0 or none. And here we have 1 and 2. It says for methane, there is an M+1 peak. And you know, I talked about that. It comes from the carbon-13. So it's 1.1%, not 1%. Oh. So the more carbons in the atom, that stronger that M+1 peak is going to come up. And here we have decane, which is 10 carbons. So look at the relative abundance here. Here it's around 10, and here it's pretty low. Because if you multiply 10 times 1.1, that's what? 11.1. So I should have said around 11. It says chlorine has 2 abundant isotopes. Let me see something real quick. So you'll see them in a 3-to-1 ratio. You can see that right here. Bromine, it's almost in a 50-50 ratio. So this would be bromine 79. This would be 81 right here. So the thorough analysis of molecular fragments can often yield structural information. Here we're taking off 15. See that? That's a loss of 15 right there. It's a loss of 15 plus 14, and that's how you get the 29. You can keep on adding, you know, another 14 will get you 43. Another 14 will get you 57. Because remember, mass spectrometry only detects charged fragments. So if they're not charged, it's not going to be able to be detected. And I show this right here for you. Your first mass loss, your 15, then your 29, then your 43, then your 57, which you'd only have CH3 left. says consider this fragment below. We have a tertiary carbocation and a primary radical. So while all possible fragments are possible and observed, the most abundant fragment is the most stable cation possible. So this would be the most stable one possible. And this would be 43 because you can count 12, and then each one would be 15. Get my calculator out. This is so they're wrong actually right here. It should be 43. It should be, let me see. 6, 9. This would be 57. Alcohols generally undergo two main types of fragmentation, alpha cleavage and dehydration. So this is the alpha carbon right here. This would be a beta carbon, but we're going to do alpha cleavage. So it's resonance stabilized. Here they're showing you a loss of 18 right here. Just want to come back to this one. 12, 12, 12. This is 36. So if they're saying that this is 57 right here, but they're saying that you have a loss of 43 then. So this right here is 43, this is 57. If you come to this example right here, they're showing you a loss of 18 right here. So that's what they're showing you. Because amines also undergo alpha cleavage. Here we see this alpha cleavage right here. And carbonyls generally undergo a McLafferty rearrangement. And they're showing you the McLafferty rearrangement here where this oxygen radical takes this proton, hydrogen, and we have this McLafferty rearrangement. Common fragments, fragment losses, methyl, ethyl, propyl, butyl, 18 is water, and then MX, where X is even numbers, and McLafferty rearrangement or ketone or aldehyde. And if you ever want to go back to the McLafferty rearrangement, it's right here. So high resolution mass spectrometry allows mass charge ratios to be measured up to 4 decimal places. It says masses are generally not whole numbers, whole number integers. You can see a proton is 1.0073, neutron is a little heavier. And one carbon 12 atom is exactly 12 AMU because that's what it's based on. They show you right here the different abundances in nature. See the chlorine, the 3 to 1 ratio. Bromine is almost a 1 to 1 ratio. Right here. This high resolution mass spectrometry allows one to distinguish between compounds that have the same molecular weight. So these have the same molecular weight, right? But we can distinguish them with mass spectrometry. It says mass spec is suited for the identification of pure substances. They're usually they're usually combined or with like a GC and LC and ICP. So they're coupled with some other instrument. It says GCMS, they give two different types of data sets. They give you your mass spectra and they give you a chromatogram. So here's your chromatogram, and from the chromatogram you can extract, the mass spectrum. So that's what they're talking about. Each peak has its own separate mass chromatogram. So maybe this one looks like this, and this one might have a big peak right here. So I'm just trying to demonstrate that each peak will have different mass spectra possibly, because they're probably different compounds. And sometimes you'll have overlap where the same peak overlaps. Now this is getting more complicated, and then you have to extract out the data. So to be analyzed by electron ionization, substances generally must be vaporized prior to ionization. ESI is more common for LC. The high voltage needle sprays a liquid solution of analyte into a vacuum causing ionization. It's a softer ionization technique. That means it's not going to fragment the compound as much. So mass spectrometry is often used to determine molecular formula. To saturate hydrocarbons, follow the formula below. If you put 1 here, you get C1H4. That's methane. Unsaturated would mean we'd have some type of double bond. So degree of unsaturation, a pi bond or a ring. For every degree of unsaturation of a compound, the number of hydrogens is reduced by 2. They're unsaturated because now they contain either a double bond or a triple bond. If they'd be saturated, they'd be here. So this is saturated. It's saturated because it contains the highest number of hydrogens. And you can see that we have 2 less here and another 2 less right there. Let's consider the isomers. One has 2 double bonds, one has a triple bond. 1 degree of unsaturation equals 1 unit of hydrogen deficiency. So the hydrogen deficiency index, or HDI, so a halogen is treated as if it were a hydrogen atom. And there's an equation for this hydrogen deficiency index, and they give it to you on the next slide. And this is right here where it says hydrogen deficiency index equals 1/2 times 2C, which is your number of carbons, plus 2, plus the number of nitrogens, minus the number of hydrogens, minus X. In this case, X can be halogens. This calculating the hydrogen deficiency index can be very useful. For example, if the HDI was 0, the molecule cannot have any rings, double bonds, or triple bonds. So if it has, let's just say we calculated this right here, this should have an HDI of 4 because it has this, it has a ring. So that's it. I hope you enjoyed this lecture. Remember, the chapter 13 homework is due today. I'm going to send an announcement out for that. Enjoy your day, and we will work on the chapter 14 homework tomorrow. So let me stop. I have a